Hey guys, this is Josh, and on behalf of Academia on Demand, I am bringing you, I promise I am not lying, absolutely the final video on the covalent bonding part of this channel. So, in the last video, we were introduced to one particular exception, and this is the title of this video is the exceptions to the Lewis and VSEPR General Rules, and exploring a little bit more on all the advanced ideas behind drawing these structures. So in the last video, we were introduced to the idea of delocalization. And this idea was presented through the molecule ozone, which we actually also labeled as a bent trigonal planar. So, and what we discovered, if we redraw this structure, the structure of this molecule, and we draw out this oxygen, the oxygens, what we discovered is that this delocalization, which is the spreading of a single molecular orbital over more than one particular bonding position, what we discovered is that this delocalization provides more energetic stability for this particular molecule. So this provides more energetic stability, and this is because of the idea that both bonds, as we said in the last video, both bonds acquire a greater strength and a lesser length, and because the bonds are both equally stronger, because as we discussed before, the reason for delocalization is because there is no more energetic state. And when we're talking about the application of double bonds in order to provide energetic stability to the central atom. So when delocalization occurs, let's take a step back for a second. We can say it occurs when no more stable state exists. And when I say this, I don't mean that there is no more stability. That's be a misinterpretation of what this means. This means that there is no state that is more stable than another state. And that's why here, whether this oxygen has this double bond or this oxygen has the double bond, both of them have the same electronegativity, so therefore it would seem as though both of the states are equally energetically stable. And that's why this molecular orbital, the two electrons that occupy it, are able to delocalize in this thing called a superposition over the two bonding positions, over the two extreme bonding positions that can occur here and here. So this is the first special case of this idea of drawing Lewis structures, and the reason again is to create more energetic stability, because if both bonds are stronger, this makes the molecule itself more stable. So now another exception that we are going to talk about is the exception of this idea where it is the central atom. So central atom experiences what is called an extended octet. What exactly this means is the idea that normally when there's a central atom, so let's draw methane, central atom carbon with 4 hydrogens surrounding it. When this central atom carbon, when it has bonded to 4 things, it is energetically stable and is not able to bond to more than 4 things. Well, in some elements in the third group are able to do this and maintain their energetic stability. And the reason for this is because of their d orbitals. D orbitals that are empty d orbitals. Empty d orbitals. And so, because these d orbitals are empty, they're able to acquire electrons. So, for example, if we take the element sulfur, and we were to say, what if it were to bond 6 times? So if we know that sulfur its valence electrons, its most outward electrons are in the third energy level. Specifically, the highest energy electrons are in the 3p sublevel. The 3p sublevel. What this means is that if its electrons are contained in the third energy level, that means that it also has access to potentially a 3d orbital, because even though the 3d orbital is actually 2 energy levels higher than the 3p orbital, because of the idea that both of the orbitals reside in the third energy level, when bonding, sulfur has access to these 3d empty orbitals. So, for example, sulfur is able to bond to fluorine 6 times. SF6, or what we would say sulfur, we would call this sulfur hexafluoride. Hexafluoride. And this is a naming system in covalent bonding in which anytime that there is a specific number of molecules, certain number of atoms that are bonded to a central atom in a molecule, you place certain abbreviations before the atom itself. So here, because there's 6 fluorines, we would say hexa. And if there were 4 fluorines, we would say tetra, in that nature of things. Okay, so we have this idea of the name, and then the structure. We know sulfur is the central element. So if we draw out sulfur, and this actually, the drawing of this molecule takes place very simply actually. If we draw a single bond with all of the fluorines, let's keep drawing our single bonds, what we will find is that this molecule, all of the atoms in it are actually completely satisfied with the single bond and then added lone pairs on the fluorine. And the reason why sulfur, as we said, the reason why sulfur is able to be energetically stable in this state of 6 bonds is because of the idea of the extended octet. This extended ability to accept the fluorine's electrons. So here, though there are four molecular orbitals that fill up the 3s and 3p atomic orbitals, like the place of those orbitals where they would be, these molecular orbitals fill those up. These are 8 electrons, but in the final two orbitals, these electrons in those orbitals are what would occupy the 3d atomic sublevel. So if there was complete 3s, 3p, and you were to draw out the 3d sublevel, 3d, we were to make 5 boxes because we know there are 5 orbitals, these 4 electrons would occupy these energy levels in some way. Okay, so these orbitals in some way. And though in hybridization we actually learn exactly how this way is, the point is that these molecular orbitals, so these pairs of electrons, will occupy the spaces that were normally reserved for 3d orbitals. Okay, so that is the first set of exceptions that we will be talking about in this video. And as you can see, I've gotten a new setup because I thought the setup in the last video was just absolutely atrocious, and I couldn't stand to keep doing what I was doing with that squeaky table and disgusting marker that wouldn't erase. So I decided to change my setup. The whiteboard is much higher quality, so we shouldn't have any erasing issues like before. Okay, so the next exception that I want to bring to your attention is the idea of dative bonding. And this isn't as much a structural exception as it is a charge exception. So dative bonding. It's not dating bonding. These bonds are not dating, but dative bonding. And this is bonding in which one species, one element, one atom, one species donates both electrons in the bond. Sees donates both electrons. And as we said in the first covalent bonding video, usually the molecular orbital that is formed in any bond is made up of one electron from one atom and then one electron from the other atom. But here, in dative bonding, when this occurs, one atom donates both electrons. And what this creates is usually a situation where the resulting molecule takes on a charge. So we'll actually take a small glimpse into the world of acids and bases, and we will talk about the interaction of ammonia with a hydrogen ion. So if we got our ammonia molecule, we've got our lone pair, and then our three hydrogens, and there's a lone pair here, and then a hydrogen ion comes along. This often happens when ammonia is dissolved in what is called an acid solution. And an acid solution is a solution that essentially contains hydrogen ions. In a simplistic form, it contains hydrogen ions that just float around in this what we call aqueous solution, this solution in which there are chemicals dissolved in water. So this situation that occurs could actually very easily occur in a chemical laboratory. So if this H plus ion, this hydrogen ion, were to interact with this lone pair, it would have the tendency, because this has at least a partially negative charge, because obviously this isn't like an ion, it's not a charged molecule or anything of that such, but this area of electrons, the lone pairs right here, it has a partial negative charge, what we called in the last video a delta negative. A delta negative because there's a high electron density, a high density of negative charge in this area relative to the other areas of the ammonia molecule. So because this is a positive ion, it has the tendency to attract these electrons. And what can actually happen is that these electrons can become so attracted to the positively charged hydrogen ion, which by the way is only a nucleus, which by the way is only a one proton nucleus, no electrons, no protons, so it has a very strong ability to on its own attract negative charge. It can result in a molecule that has a tetrahedral shape. And you would think, oh, that's great, because this tetrahedral, now there's no more repulsion of these higher energy electrons, so therefore it must be more stable. Well, the problem is not really, because what happens when this hydrogen ion essentially adds itself to the ammonia molecule, the resulting product takes on a positive charge. And this means that it is charged. It is like an ion. It is what we call an ammonium ion. Ammonium, resulting from ammonia. Ammonium ion. And this ion, as we will see much later, has an abundance of properties. It is able to react with water in order to form back the initial ammonia molecule and give away this hydrogen ion. It can do lots of different things like that. And as we will see later, this actually plays a strong role in developing what we will later come to know as acid-base theory. So now the next little exception I would like to introduce you to is the exception of the dimer molecule, the dimer bonded molecule. And the reason why I'm doing these exceptions, I want you to realize, is that by doing these exceptions, you're coming to have a deeper understanding of exactly not only just Lewis structures and the drawing of molecules, but also just how chemicals work when they interact with each other. So then in future videos, when we get into organic chemistry, when we get into acid-base theory, we have a strong intuition of exactly how these molecules may bond. So I'm giving you lots of different experience. Almost, you can call it almost like a training day if we were talking about jobs or employment. and then I am giving you lots of experience to go forward into future lessons with. So now the next thing as I said, we are going to talk about dimer bonding. And dimer bonding occurs when two subunits of a particular molecule bond together in order to create greater energetic stability. So two subunits bond. Exclamation point. Okay, so the example that I'd like to give to you today is the example of Al2Cl6. And as we know, if we look at this from a division perspective, if we divided both these numbers by 2, we divided both of them by 2, we would get AlCl3. And in this dimer situation, this thing we call a dimer, this is the subunit. The subunit is AlCl3. But because of the idea, as we talked about in previous videos, of this dual concept of ionic and covalent character, though this dimer molecule could exist in AlCl3 and have a sort of almost an ionic type of bond where this aluminum, which has a +3 charge, gives away 3 electrons, the chlorines accept them. But because of the change, the difference in electronegativity that is actually relatively low, there is a high degree of covalent character as well. And that is why often this molecule is only seen in this form, in its dimer form, where there are two, when you see dimer, that's two aluminums. So if you draw out one AlCl3, if we draw out one of them, AlCl, and AlCl, and this is actually exactly the same thing as the boron trifluoride that we've looked at as an exception in so many other videos. Many group 3 elements, such as aluminum, such as boron, have this ability to only bond to 3 things and thus form a trigonoplanar. But they are even more stable. They are even more stable when they are bonded, see aluminum, in this way. So if we want 2 aluminums, what can actually happen is that we can draw out a structure in which this chlorine, if we draw out chlorine, and chlorine, there's actually a situation here in which the molecule gains greater stability if this lone pair that would normally reside here bonds with this aluminum center, and that this lone pair that would normally reside here bonds with this aluminum center. And see how now we almost have made like a checkerboard where we've got our aluminum, our chlorine, aluminum, chlorine, so like black, white, and that sort of idea of that the alternation of the elements in this chemical compound. And this is exactly what a dimer is here, because of this bonding of this lone pair on this chlorine to this aluminum, and that chlorine lone pair to this aluminum. The aluminums have gained a complete outer energy level. They have gained 8 electrons, and so this makes them more stable. And this is why this idea of aluminum bonded with chlorine is often only seen present naturally in this dimer form in nature. So that is another thing I'd like for you to keep an eye on as we head into the future with this channel. And now here I am going to actually erase the entire what we have done here. Then we are going to do one final tricky example before we wrap up for the day and don't talk about this VSEPR Lewis thing specifically to a video ever again. We might allude to it, but we've learned it. We have a lot of practice with it. I've made countless videos. Now we feel confident knowing that we know exactly what this idea is. We know exactly how to deal with it. Okay, so the final exception that I would almost like to introduce you to is the exception of the NO2 molecule, the NO2. So nitrogen, NO2, or nitrogen dioxide. Nitrogen dioxide. And so I'm going to ask you, how are we going to make this molecule's Lewis structure? So as we know, systematically, the first thing we always do is find the number of valence electrons we have to work with here. So we know there are 5 in nitrogen, 6 in oxygen, 2 oxygens. That makes a total of 17 electrons. 17 electrons. Okay, so the first thing that you could do here is you could just start drawing out the structure with the nitrogen in the middle, oxygen surrounding. But first I would like to bring to your attention something a little bit interesting. So we can see here, obviously there are 17 electrons. And what implications does this have? Well, as we remember from the VSEPR theory, one of the meanings in the acronym, the EP part, EP, represents electron pairs. Electron pairs. And so, as we know, pairs means 2. Pairs means 2 just by common linguistic sense. So, pairs means 2. Well, if there are two electrons in each pair, and we want pairs in order to make the molecule more stable, how are we going to make pairs, even pairs, out of all 17 of these electrons? Well, the answer is that you can't, because you can't divide 17 by 2 and have an integer answer. It's actually 8.5, which means that somewhere here in this molecular orbital that we are going to create, there is going to be only 1 electron. And this seems really foreign. How could there possibly be only 1 electron and it be stable? This is outrageous. Josh, you are ridiculous. So I'm going to show you how. Okay, so the first thing we are going to do, as always, draw our nitrogen in the middle, and then draw our oxygens to the outside, and draw them with 3 lone pairs of electrons on their external energy levels, and then we'll see where we're at from there. Okay, so if we just have this structure, we can see clearly that these oxygens have 6 electrons on each of their outer energy levels that they're just lone pairs. They're not bonding with anything. So that's 12 electrons, and then 14 and 16. So we have 1 electron left. And as we know, the only element that isn't stable here is nitrogen. So if we put this 1 electron right here, normally when we have lone pairs, we represent it as a line, a line that is a area of electron density. But here, that we can only have enough electrons to put 1 there. But this 1 electron, this half-filled atomic orbital, because as we know, lone pairs reside in atomic orbitals. This half-filled atomic orbital still does to a large part repel the other bonded pairs of electrons. So the new structure here, we can draw it out as nitrogen with the 1 electron, and then the oxygens, And so this creates a situation in which the nitrogen has about 5 electrons that are bonded to it. But this still is a far way from it being energetically stable with 8. Okay, so how could we solve this issue? How could we make this better? Could we solve this breakup between the nitrogen and the oxygen? Okay, so as we know, as we've seen before in the ozone, there is an element of delocalization in this molecule, in which the reason is because either of these oxygens could give a double bond and have this structure. And this can be shown if we draw out the other extreme form of the double bond, which would be nitrogen with the single bond here, and then the double bond on this oxygen. And see, since neither of these states is more stable than the other, what is most stable, therefore, is a state, kind of in-between state, as we said before, this idea of superposition. 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 Let's draw a big arrow. Big arrow. Okay. And what we get here finally is nitrogen with a single electron, and then with one single bond on each oxygen, and then a delocalization of a molecular orbital over both bonds. And as we remembered, let's just refresh one more time. This delocalization has an equal effect on both bonds and therefore creates a state in which both bonds are more stable. So now this is all of the exceptions that I wanted to bring to your attention to end this covalent bonding theory series of videos. More stable. And now I'm going to leave you, and tomorrow I will be talking about hybridization and how this idea of Lewis and VSEPR that we have been studying here, while it makes sense from a practical standpoint, it is not necessarily 100% accurate. We are going to understand why. So if you like these videos, you should subscribe to my channel as well. Visit my website that is given on the link in the bottom of this, below this video screen. So I'll see you all guys later, and hopefully you will see me tomorrow. Alright, have a good night.